Next up for our talk is my good friend Sen Nordstrom. I used to work with her when we were at Bell Canada together, and the information that she mentored me on and taught me actually helped me pass an interview. So hopefully some of the information that she passed on to you today will help you in your careers. Sen is an optical engineer at Equinix and working with optical systems at scale, but today her talk's about fun with optical systems, so let's enjoy it.
Okay, as Mark mentioned, I'm Sen Nordstrom, and I want to talk about fun with optical systems. Your definition of fun may be different from mine. I think there's a lot of value in knowing more about optical, even if most of what you do is packet. And I want to talk a little about that. Your level of fun may not be exactly as described. Some terms and conditions apply. You all carry pagers, so you understand how it goes. Standard disclaimer, Equinix trusts me to move photons around without letting them fall out of the cable. Nothing I say should be viewed as their opinion. Also, nothing I say should be viewed as advice on running your production network. You should do more research before you take anything from this into your network. I think every slide deck should have some cute animals. These are my pets. Pavot, as in Grande Pavot with the spots, and this is Whisper and Willow. There's been a lack of pets today, so I'm glad I included those. By day, Equinix, as I mentioned, trusts me to work on stuff like this. I do deployment engineering, so taking designs that work in a spherical network in a vacuum and making them work in the actual world that exists. So yeah, by day I fix stuff like this, and when I'm not doing that, I fix stuff like this. If you see me around at some point, ask about heritage trains. I think they're pretty fascinating too. Show of hands, experience level with optical systems. Any experience with fiber optics at all? Plugging two routers counts. Okay, good. Troubleshooting optical systems with anything other than show commands, so power meters, OTDRs, et cetera. Okay, good. I was a little worried that all the hands would be up through all of these, and then my talk is a little basic. WDM at all? CWDM, DWDM? Cool. More complicated optical transport, line systems, ROADMs, amplifiers. Okay, good. Excellent. This is a good level then, I feel like. Nobody likes layer one. It's that annoying layer down at the bottom of the stack somewhere where your pager goes off when something goes wrong with it. But there's nothing interesting down there. It just happens down there somewhere. It's someone else's job. But I think some of us really do like layer one. I think it's great. It's that interesting layer down at the bottom where the network collides with the real world. Sometimes it is really annoying because you get paged in the middle of the night when there's a backhoe or something. But I think it's pretty interesting, and I think there's a lot of value in understanding it more, even if you're not directly working on it. I want to talk a little, starting with fiber optic, the physics side. Whenever I've talked about, and I hear this from other optical people too, optical networks in general, people will say, well, you talked about like 90% optical and 10% networks. And that's a little true of this talk. It's half an hour. There's only so much you can fit in. And you can't really understand the network side without the optics side. There will be another talk later today, I think at the end of the day, about open fiber systems. So that'll sort of fill in some of the gaps from this one too, I think. Okay, so basically, how does fiber work? It's a very thin, 9 microns or 50 microns usually, strand of glass, so thin that we can bend it, which is why it's so useful, surrounded by a slightly different kind of glass. And if you put light in the end of the fiber, it'll bounce off that junction between the two different kinds of glass and just keep bouncing kilometers and kilometers away, unless you bend it too much. The light has to travel at a very shallow angle through the fiber. So if you bend the fiber too much, all of a sudden that shallow angle hits a 90-degree bend and it leaves the cable. And then you get loss. We'll talk about that a little more. I have some live demos. We'll see how that goes. But that's basically 101, very basic. How does fiber work? Two main kinds, which I imagine you're familiar with, single mode and multi-mode. I pretty much only work with single mode, so I'll mostly be talking about that. Single mode fiber, the core fiber, that glass strand, is very, very thin, about 1/100 of a millimeter in diameter. That makes it very good for long distances, but a little harder to manufacture and work with, so it tends to be more expensive. Multimode fiber, much bigger core, 50 microns instead of 9. Cheaper to manufacture, cheaper, easier to work with. But the problem with it is when you put light in, because the core is so wide, light can take many different paths down it. So you may have one light ray zigzagging like this inside the fiber and one taking a longer path, which means that by the time it gets to the end, one of those, the one that's been going like this, has had to travel a lot further to get the same distance. It means that the sharp pulse that you put in at one end gets very smeared at the other end, and limits your speed that you can run, because those pulses will start to run together. You can't figure out where one bit ends and the next begins. So it's usually used for shorter distances within a data center, within a floor, within a cage, something like that. Historically, it was used more. Now single mode transceivers, cables, everything have gotten so cheap that I'm seeing a lot less multi-mode. The company I work for has pretty much eliminated it for running outside of a cage. If you want to run anything in our infrastructure, it's all single mode now. So pretty much everything I talk about will just be single mode. I'm sure you've seen the visible spectrum from violet up to red, and then there's ultraviolet down there and infrared somewhere over here. But I feel like as optical engineers, we think of it sort of more like this. There's visible spectrum down there. It's useful for something. We like being able to see stuff, but not really useful in networks. There's some Rayleigh scattering and other physics things that make it not that useful. So pretty much near infrared and mid infrared is where all of our day happens. So 650 nanometers up to 2000-ish, a little under that. Can anyone name some of the most common wavelengths that you're probably using in your network today? Yep, that's probably the most common by far. 850, yeah, for multimode especially, 850 nanometers. 1550, there you go. Okay, yeah. So most common, I think, probably 1310, and then 1550 if you want to go further, 850 nanometer for multimode. Does anyone know why we use those ones? Those are some weird numbers. Why not just use all of the wavelengths in between? So this is a very busy graph, and I feel like at some point I should probably redraw it. But you can see the graph, kind of a bathtub shape. Higher on the graph is worse. So higher on the graph is more the light is leaking out of the cable, the higher you go. So the low end of the graph is up at like 5 dB per kilometer or worse. That's getting pretty close to visible light, which is why we can't really put visible light through fiber. CD players and home theater stuff uses visible light, or historically has, but it's going a few meters. Above that, you don't really want to do that. And then there's these peaks in black, which are water peaks. Ions or hydroxyl groups get trapped inside the fiber. Water essentially gets trapped in the fiber as it's manufactured, which causes it to absorb a lot of light at those peaks. So all of the common frequencies we use are chosen to fit in between those peaks to get the least amount of loss, so that we can run signals really far and not have to worry about it getting absorbed by these water molecules. There are newer kinds of fiber, more expensive kinds of fiber called zero water peak that eliminates this. But often, especially if you're running on someone else's outside plant, you don't get to decide the kind of fiber. You may be running over a span with lots of different kinds of fiber. Probably not all of it is this kind. So everything is really designed to fit in between those. And then as you keep going to longer wavelengths, you start getting other physics effects, infrared absorption loss, that mean we can't really run much over 1.6-ish micrometers, 1600 nanometers. I'm going to talk a little bit about optical networks. This is going to be a very brief overview, but so the most basic optical network you might have, you have two buildings. They're, say, 35 kilometers apart. You rent some dark fiber from someone, you put some ER optics in your devices, and you connect them together. Very simple, it works fine, as long as no one messes with the fiber. But then if you want to run two different routers over them, You don't have to rent a whole separate strand of fiber between them. It gets expensive. So you run each signal on a different wavelength, combine them at one end, split them out at the other end. It's like the flashlights, the colored flashlights experiment when you're a kid. You've got a red flashlight and a blue flashlight. You mix them, you get purple light. Then at the other end, you split them back out. That's WDM. CWDM is coarse WDM, coarse wavelength division multiplexing. So the frequencies are spaced pretty far apart. It's cheaper and easier to use. The physics gets in the way a little less. DWDM, or dense, you can pack things a lot closer together. You can fit a lot more over the same fiber, but physics starts getting in the way a bit more, and everything gets more expensive because you're trying to fit different signals very close together without them interfering with each other. So, yeah. This setup can pretty much be called an optical add-drop multiplexer as well. If you were working back in the T1 days, or maybe still, if you were using channelized T1s, CSU DSUs, you could get add-drop CSU DSUs, where you could take some channels off a T1 at a site, drop them off, and then carry other signals on to another site or another device in the site. This works exactly the same. You can transit some wavelengths from site A to site B. If you had a site C, you could drop some off there and continue some on to the next site. The problem with that is, it's great, it works fine until you want to change something. Each of these muxes has a port for each wavelength. So 1550 will come out this port, 1560, this is simplified, but will come out a different port. If you want to change anything, you have to roll a truck or get someone on site to be moving cables around and stuff. Also, when you're moving cables around, that's error prone, you could bump a cable you don't mean to, et cetera. So you really want to be able to change all this in configuration, even though it's changing the actual flow of light around the network. So this is an architecture for a remotely operable optical add-drop multiplexer. We just keep adding letters to the acronym every time it gets more complicated. So these symbols, the lambda icons and the blue squares, are wavelength selective switches. So under software control, you can change whether each individual wavelength is going through to the next site or getting dropped off at this site, which means that if you move a router from one site to another, or you need to change which wavelengths things are working with, you can just reconfigure it in software. Often GUIs, optical vendors really like GUIs a lot more than CLIs, which is pretty jarring if you're used to the packet world. You go from iOS and JunoS to all these Windows GUIs, but just a different way to get used to. But you can configure this wavelength I want to drop off at this site, this other one I want to pass along. And it gets a lot more complicated from here too. There are different routing protocols so that you're not saying, I want this wavelength to go from site A to B to C and then drop off. You're just saying it needs to go from here to here, figure it out. I want to talk a little more about failure modes too, because we're talking about the real world where things fail often. I'm sure everyone is familiar with the North American fiber-seeking backhoe. This is a slide from Reddit. Backhoes, I feel like we refer to as like the default, my network is down because of a physical break. People will refer to the backhoes. Please call before you dig. Call your local locators. Here it's Ontario One Call. They will come out for free. If you're digging to put a fence in your backyard, call them. They will make sure you're not digging through fiber. Still happens constantly that stuff gets dug through either because they didn't do a locate or because they dug where the locate said there was fiber, or because the locate is wrong, because sometimes drawings don't match reality. Often drawings don't match reality. Other faults. This happens a lot more than you might think. Dump trucks leaving construction sites and tearing down spans of aerial fiber. These, I don't know what you call them. They're like dumpsters that come off the back of the truck. They'll leave a site having dropped a dumpster off with their arm thing up, and this one, this was like 8 or 9 years ago in Toronto, hit a bridge, and that duct on the bridge, of course, had our fiber in it. So Yeah, and dump trucks leaving construction sites, tearing down aerial fiber as well happens a lot. So physical damage kind of things. Extreme temperatures. So this was, I think, Front Street a few years ago. Manhole caught on fire, burned a bunch of fiber, caused multi-day outage for a lot of systems. That's why a lot of optical networks have multiple routes, as packet networks tend to. Especially after fires, there's a lot of safety stuff that has to be done to get back in there, so it can easily be a many-day outage. Cold as well. Splice cans, which are like the black things you see hanging on aerial fiber, and there's underground versions, are supposed to be sealed so that water can't get in. Sometimes caps don't get installed properly after work is done, or the seal fails, or there's a manufacturing fault, or for whatever reason, water can get inside. And when that water freezes, it squeezes the fiber because the water is trying to expand in an enclosed space. It'll squeeze on the fiber and cause extra loss because you're bending the fiber. That light is now leaving the core where it's supposed to be. You can actually, when this happens, sometimes see a correlation. If you look at the weather report and your fiber loss in a span of your network, you can see a correlation between the weather and your network. So this is kind of an extreme example of the real world colliding with your network. Another few causes. This one happens so much more than I would have thought, especially in the US right now. Fiber getting shot, aerial spans. Either people are shooting guns into the air or missing whatever they were aiming at. And probably every couple weeks on the fiber splicing groups, you see someone showing what bullet they were removing from their fiber today. Squirrels, chipmunks as well. There were some different jacketing, eco-friendly jacketing being made at different points that was apparently delicious. And squirrels and chipmunks and things really started getting into eating a lot of it, which caused problems, still causing problems. And then this one is a little hard to see. It's a capture out of a video, but people stealing fiber. Copper theft has gotten to be a huge problem. And it's not obvious that fiber isn't copper or that it doesn't have resale value. So people will tear down aerial fiber and even underground to try and sell it and make money. This one, they hopped up on a truck, cut it with a Sawzall, and just pulled it down off a couple spans. We had an issue late last year, I think, where they attached it to a vehicle and drove off and pulled 18 span down. And then, I won't name the carrier, but as the carrier was on site to repair it, they had all their equipment staged and went for, I don't remember if it was a break or they had gone home and they were coming back the next day. And all of the fiber that they had staged, the big spools, got stolen. So they had to then source a third set of fiber to replace it. So it's becoming more and more of a problem. Even in underground now, stuff's getting stolen out of splice pedestals and stuff. Moving on to inside plant failures. This is stuff that you probably deal more with day to day. You can see port 6 here has completely pulled out of the strain relief boot and is just being held by the core and some strands of Kevlar there. This is causing it to bend pretty significantly. This was fine until someone opened the door on the rack, and then just that vibration of the unsupported fiber started causing a bunch of alarms. So any kind of bends sharply, and I had never seen this specific failure mode before where the whole jacket had pulled out. And then port 7 and 8, it's a little hard to see here. I had to crop it tightly because there's just confidential information everywhere, as you can imagine, are pretty much going straight down. These had gotten hooked on something else as they were installing a connection later and just pulled really hard straight down. Again, this was fine until some vibration happened over the years, and then it was less fine in the middle of the night, as often happens. This one, so optical vendors really like putting doors on equipment for some reason. Optical equipment always has just massive patch cables in the front because a lot more of it has to happen in physical changes versus logical changes. Depending on the fiber you're using, those doors can squish the fiber. So in this case, you can see the hinges over on the left. These ones at the bottom are fine. The strain relief boot is pretty short on them, so they're not going to interfere with anything. But as the different ones got installed over the years, someone put some long boot ones in. And you can see here, they come out and then they go straight down. The door has been pushing on them over the years. And again, this was fine day one, 8, 9 years ago. But every time you open that door and close the door, it gets pushed on over and over again. And then at some point, you're going to start either getting alarms for high loss or you're just going to have an outage. So doors on things, even doors on cabinets, depending on how close your equipment is to the front, can really cause some significant problems there. Dust, dirt, contamination. Because the core of the fiber is 9 microns in diameter, usually for single mode at least, it's 100th of a millimeter in diameter. Any tiny particle of dust, scratches, just touching it, oil from your hand will get on it and block some of the light. Especially with oil and things, if that fiber is contaminated and you then switch it to another port, you move the contamination around and just spread it around. This can be a significant problem. And so Viavi is a major test equipment vendor. I'm not advertising for them or anything. They just have this campaign called Inspect Before You Connect. They say that you should buy their fiber optic microscope, which they make good equipment, and always inspect connectors before you connect them. Realistically, I know none of you are probably inspecting every connector with a microscope before you plug it into your router from here to here. People are being pointed. Mr. is, okay. Okay, very few of you probably are inspecting before you plug into your router every single cable. I think clean before you connect is good advice, even if you're not going to inspect every connection. Keep some cleaning wipes around, keep a cleaning tool around, and especially people clean patch cables all the time. People don't clean the patch panel ports or the transceiver ports, things like that. If you don't clean both ends, then your clean patch cable is just picking stuff up from the other end. Ideally, do inspect before you connect, especially if it's a cable that is going to be carrying a lot of traffic. If it's WDM and you're carrying, 20 800 gig connections over it, inspect it before you connect it. Double check that there's no contamination, clean it, check it again, then plug it in. Also stuff if you think it's going to be there for a long time. If you don't want to come back and touch this cable for 10, 15 years for whatever reason, make sure it's really good day one, because then you don't want to have to come back to it later. All right, we all know how live demos go, so we'll see how this one works out. It's fine. But live demos do sometimes go badly, so we're going to see how well this works. This case has a little set of fiber spans in it and an OTDR. So we're going to be looking at this 1 meter span in the middle. I've got some various impairments, and we'll take a look at that and see what they look like. So basically an OTDR, I don't have a slide for this, I should have done that, sends out a ping of light down the cable, and as light travels down the cable, little bits of it bounce back constantly. If it hits something, an impairment of some kind, more of it will bounce back, or less potentially, depending on the impairment. And we use that to figure out both where the problem is and what the problem might be. If there's a connector that's not seated properly or some dust, these can look different. And because we know how fast the signal travels in the fiber, you can basically correlate time and kilometers. So you can see it bounced back after 20 kilometers. So we know, looking at our map, that's at this site. So I'm just going to switch this over. See what I was saying about live demos? There we go. OK. So this is zoomed. Nope. There we go. That's better. So this is VNC'd into test equipment in here. This is zoomed in on that 1 meter segment in the middle. So we've got 2,200 kilometers of fiber. Fiber is really small, so you can carry a couple kilometers of it easily. 2,200 meters, and then some patches between patch panels, and then another kilometer span. Let me just pull this out. So right now, I don't know if you can see from there, we have this coming, the input fiber, and then this one's a different color. So you can see here, it comes in at just over 0 dBm. Lower is more loss. There's a bunch of reflections. Ignore the reflections. Those shouldn't be there. One of my spans of fiber, as I was moving it here, had some issues. So the bouncing is fine. But then on the other side, you can see it's like 4 dB lower. So this is multi-mode connected to single mode. There's a few situations here that I'm going to show where connecting different colors together, if the things on either side you're connecting with fiber are different colors, you should know why that is and have a very good reason for doing it. Usually that means that there's a problem somewhere. So I'm just going to start this real-time acquisition. There's a bunch of clicking happening here. With multi-mode connected to single mode, it's a little hard to see on VNC, but as you move it around, you can see this line. Oh, yep, there. A bunch more loss now, going down a lot more. This can happen if you called someone and asked them to make a patch cable or plug in a patch for you. You're connecting in a data center that you don't necessarily know is some of the structured cabling, multi-mode or single mode. And as it moves around, you get significantly different amounts of loss happening. So this might look okay day one again, with only a few dB of loss. But then someone comes in and wiggles something very slightly and causes a more significant problem. So I want to change this out for a different kind of fiber and do one more quick demo with this. As we were talking about earlier, bending fiber causes a big problem. I'm also not inspecting or cleaning before I connect this, but this is just a lab. This is a do as I say, not as I do moment. So this is single mode to single mode. This fiber has a little bit of loss. You can see it comes in at just over 0 and leaves it just under 0 because it's been bent like a million times at this point. It's lab fiber. You can see that this kind of bend is pretty much fine, not really causing any problems. This is probably as much as I would want in a production network. And then if you keep bending it, you start getting a little more loss. And then once you cross a certain point, it starts going down pretty significantly. So especially if fiber gets caught in a cabinet door or caught on a different cable and you're pulling it down, you can really start to get 5, easily 10 dB, and we're pretty much down to where your network is probably having significant problems at this point. So yeah, don't bend your cable, and fiber is cheap, outages are not. If you do bend it like this, it does come back when you restore it to normal. I would never trust this fiber again. If that's happened to it, replace your patch cable. You should keep spares around. I know I said don't trust me with advice on running your production network, but that's my opinion. Once fiber has been damaged in any way, it's not expensive, unless if it's subsea, it's expensive, but then you probably have experts. Patch cables are cheap, just replace your patch cable. All right, that's pretty much it for me. Takeaways, this was more, this is why I think this is interesting. There's some interesting physics here and interesting real world stuff happens. But I tried to come up with some takeaways. Inspect your cables before you connect them. Good job inspecting them before you connect them. Most people don't. And I've had people complain that it takes longer to do it that way. But I think it takes longer to do it that way at first, and then you don't get woken up in the middle of the night 6 months later. So I think it's worth it. Fiber's cheap. Just replace your patch cables. A lot of sites will just replace them by default after one use. If you pull it out of production, get rid of it or put it in your lab. If you have fiber troubleshooting tools and some spare time, play with them. Get familiar with the tools and how they work and how different outages and impairments happen. I think it's worth using your tools when you're not in a crisis situation. And yeah, layer 1 has a lot of interesting stuff. It doesn't just cause outages, it causes fun and interesting stuff too. That's it for me.
We have 6 seconds if somebody wants to make a lightning talk question. But no, we can take a little bit more time. We're going into a break after the next talk, so if anyone wants to run up and ask a quick question, feel free. My contact information is here on the World Wide Web or Gopher Space if you need it.
Hello, John
Hello.
Mister from Torx. So not so much a question, great presentation. 100% true everything about especially the fiber inspection, the cleaning. I personally manage over 1,000 connections that we have with patch cords everywhere, and it is unbelievable when you see what's on the surface of these fibers when you take it out of a package. I guarantee you 10 to 15% of them magically have something on there all the time. So I cannot stress enough how useful this is.
It doesn't matter if you, like you said, if you just took it out of the package, definitely at least try and clean it. I would say inspect it as well, but yeah. Thank you.
Kevin Bloomberg. This is not a Torx question, this is a personal question in terms of jacket sizes. So 9 millimeter, 2 millimeter, 3 millimeter. You know, bend radiuses where they say you can do loop-de-loops on pencils and all that. Is that just marketing garbage, or is there actually a fundamental difference in what the tolerances of some of the fiber is?
Some of it is marketing, some of it is actual tolerance differences. The things they tell you are the things that they can guarantee it's going to be good to. A lot of it will tolerate bending much more than that, and this is all bend-insensitive fiber, which is not insensitive to bending, it's just a lot less sensitive to bending. There are definitely degrees of bend sensitivity, bend insensitivity. I would say always follow whatever manufacturer recommendations are, because those are the ones they're going to guarantee are going to be good. You can probably bend it more than that, but at that point you're taking a risk with it. And there definitely are thicker jackets, thinner jackets, different bend radiuses, and it does make a difference.
Thank you.
Thank you.